Hello students, this semester we are having a course probability which is for 3 credits. In this very first lecture we are going to just cover basic definition, concept, examples to understand the concept of probability. We will explore sample spaces, events, probability axiom and some fundamental rule for calculating probabilities. So the dimensions of probability theory are sample spaces, events, probability axioms, and along with this we are going to calculate probabilities of very simple examples. So the very first question, what is probability? Probability is a measure of likelihood that an event will occur. It is quantified as a number between 0 and 1, where 0 indicates impossibility and 1 indicates certainty. What it means? It means if the probability of an event is 0, that event is called as impossible event. Means that event cannot occur. And if the probability is 1 of a particular event, it indicates that the event will surely occur, means it will certainly occur. So the probability lies between 0 and 1. If the probability of an event is 0.5, it suggests that there is an equal chance of event occurring and also of not occurring. So probability is very useful concept in our day-to-day life also. It is widely used in statistics, mathematics, science, finance and artificial intelligence. Now this picture will clear the uh, value of probability and the type of event uh, associated with it. Now here in the innermost part, this is the probability 1. So what it indicates? It indicates certain event, means sure event. This green part is indicating high likelihood, means if the probability is less than 1 but near to 1, then the event will almost occur. Now this is the next region which is for equal chance, that is 50-50. This next region is for low likelihood, means if the probability of an event is lying in this region, then the event will occur but its chances are very less. And this last, the outermost yellow part indicate that the event will never occur. So it is for impossible events. Now the probability is associated with basically a random experiment. Random experiment is a process for which the results cannot be predicted. For example, flipping of a coin, rolling of a die, uh, uh, picking a card from a deck of cards. So all these are called as a random experiment. So what is the difference between random experiment and lab experiment? When we are performing any experiment in lab setup, then there is uh, surety about the product of that experiment, output of that experiment. But in this type of experiment, we are not sure what will be the outcome. For example, if we are going to flip a coin, then there will be either head or tail. So it is not sure that you will get head every time, or it is not sure that you will get tail every time. So this type of experiments are called as random experiment. And the possible outcomes, all the possible outcomes of a random experiment makes the sample space. So the sample space is the set of all possible outcomes of an experiment. So if this is an experiment, then all the outcomes are the sample space. These are the two examples. The first one already we have discussed. The second is a die is rolled, which is a 6-face die. So obviously each face is having one number from 1 to 6. When you throw a die, when you roll a die, you will get either one of these 6 cores. So the sample space here is 1, 2, 3, 4, 5, 6. You might have observed that sample space is a set. It is denoted by capital letter S. Now this is the corresponding diagram. Now what is the event? An event is a subset of sample space. It is a specific outcome or a set of outcomes that we are interested in. Suppose we have thrown a die and we are interested in getting only the prime numbers. Then we know that the sample space of throwing a die is having 6 numbers, 1, 2, 3, 4, 5, 6. Out of these 6 numbers, 2, 3 and 5 are the prime numbers. So in that case, that event E will have the elements as 2, 3 and 5. So event is a subset of sample space. This is the probability event structure. The outermost region is the sample space. That is, this is the complete sample space, and this is the pink region is the part of sample space which is a particular part of sample space called as an event. It may contain one element, it may contain more than one elements, but all the elements should be from the sample space. There is one more type of event which is called as an elementary event. An elementary event is an event that contains only one outcome. So if we throw a die and we are interested in only getting a even prime number, then obviously the event will have 2, and that is the only even prime number. So that event will be called as an elementary event. Now, probability is governed by a particular set of rules. These are the fundamental rules, and these rules should be followed by probabilities. So, which are these rules? These rules are non-negativity. Already we have discussed that probability value lies between 0 and 1, both inclusive. Means what? The minimum value of probability is 0. Means it is not less than 0, means it is never negative. So the first axiom of probability is it is non-negative value. Second, normalization. What this axiom indicate? The probability of entire sample space must be equal to 1. This means that one of the possible outcomes in the sample space must occur. And the next is, the third axiom is additivity for mutually exclusive events. Now the question is, what is mutually exclusive event? Mutually exclusive events means the events which are not having any point common between them. That is, their intersection is 0, or we can say intersection is empty set. Now suppose we have thrown a die, then the sample space will have the outcomes as 1, 2, 3, 4, 5, 6. If E1 is event of getting odd outcome, then E1 will have 1, 3, 5 in the set, and if E2 is for even outcomes, then it will have 2, 4, 6 as 3 elements of the event. Then obviously these two events are called as mutually exclusive events, as they are not having any point common between them. So when we find the probability of these events individually and we add them, then it should be equal to the probability of union of these two events. So this is the third axiom, that is additivity for mutually exclusive events. So these are the three probability axioms: non-negativity, normalization and additivity for mutually exclusive events. So this is the thing here represented in diagram. So this is again shown here. See, this is the event 1, this is the second event, this is the third event. And when we take the union, now see, events are again denoted by sets, and we can perform union operation on sets. So event 1, 2, 3, when we take their union, then the probability of event 1, 2, 3 is when we add these three probabilities, then their value is probability of the union. Now let us calculate few examples. First is coin flip. So here the random experiment is flipping a fair coin. We know that the sample space S is head and tail, and if we are interested in only getting head, then the obviously E will be the event with head as a point. Now here the number of sample points is 2, and here the number of sample points in event E is 1. So probability of getting head is n of E upon n of S, that is 1 by 2, which is equal to 0.5. And even if we are not interested in probability of getting tail, but it will be 1 minus half, that is 0.5. As you know that the total probability of the experiment is always equal to 1. Now let us move to the diagrammatic presentation. Here the coin is flipped and we have got head. The probability of getting head is 0.5, assuming that the coin is fair, that is it is unbiased coin, means it is having head on one side and tail on another side. And if we get tail, the probability of getting tail is again same as 0.5. This is the second example of rolling a die. So sample space is 1, 2, 3, 4, 5, 6. If we are interested in getting an even number, then event E will have 3 sample points, 2, 4, 6. Assuming the die is fair, again here we are considering the die is fair, means the 6 faces of die are having 6 different numbers from 1 to 6, and each outcome is equally likely. So in that case, the probability of getting each of these outcomes is 1 by 6. So probability of 1 equal to probability of 2 equal to probability of 3 equal to so on up to p of 6 is 1 by 6. And when we are going to have only the probabilities of 3 even numbers here, then we have to just add their probabilities, which gives us 1 by 6 plus 1 by 6 plus 1 by 6, that is 3 by 6, means 0.5. So in this way we can calculate the probability when a die is rolled and we are expecting an even number. So this is the diagrammatic presentation of that calculation. Probability of getting 2 is 1 by 6. Probability of getting 4 is 1 by 6. Probability of getting 6 is 1 by 6. Now see, all these three are the mutually exclusive events. So when we add these three, we get the probability of even number, that is 1 by 2. So the third is obviously for drawing a card. From a deck of card, we know that a deck of card is having 52 cards. So drawing a card from standard deck of card is an experiment. The sample space is, we are going to just draw a single card, so it will be 52C1. Using the combination formula, we get here n of s equal to 52, and we are interested in drawing an ace. Ace means in Marathi we call it as ekka. So there are 4 ace cards in a deck of card. So there will be 4 number of aces, that is the event E will have 4 sample points, and when it is divided by total number of cards, that is the number of sample points, then we get 4 by 52 equal to 1 by 13 as a final probability. So probability of drawing card, so this is the, these are the 4 ace cards, and here these are all cards. So out of the 52 cards, only 4 cards we are interested in. So 4 by 52 gives us 1 by 13. And as we know that by normalization axiom, total probability is always 1. So probability of not getting ace card is 1 minus 1 by 13, that is 12 by 13. So in this way, using these 3 axioms, we can find out the probabilities. Now this is same as complement of a set. We have studied set theory in discrete mathematics. There is universal set and there is some definite set, suppose set A. Then how do we calculate complement of set A? Complement of set A contains the elements from universal set but which are not in set A. The same concept applies over here. The probability of event E, if it is denoted by P of E, and we know that the probability of the sample space is 1, then probability of E dash, that is complement of an event, is 1 minus P of E. Here one example is discussed. Suppose a die is rolled and we are expected in outcome 6, then probability of getting 6 is 1 by 6. Then probability of getting not getting 6 is 1 minus 1 by 6, that is 5 by 6. So this is called complement of an event. Not rolling a 6 is 5 by 6 and rolling a 6 is 1 by 6. So both again when we add, we get the answer 1, which is the probability of sample space. Now same as sets, we can perform union and intersection of events also. So union of two events E1 and E2, it is nothing but the occurrence of either E1 or E2 or both the events. So this is called union of events. Now see here in this diagram, here it is event E1, here event E2, and this is the common part which is the intersection part, but union means either this event will occur or this will occur or both of them will occur. Now the next is intersection. Intersection of two events is the event when both the events will occur surely. So this is the intersection part of event. So here this part indicates that both event E1 and event E2 are occurring. Now this is the general addition rule. Probability of E1 plus probability of E2 minus probability of E1 intersection E2. This is same as the inclusion exclusion principle which we have discussed in set theory. So here P of E1 union P of E2 is given by P of E1 plus P of E2 minus P of E1 intersection E2, and this rule can be extended to n number of events. Now we are having additivity axiom as well as the rule for addition of probabilities. So according to the situation, we have to select the correct rule. If the events are overlapping, then we have to use the rule which is similar to inclusion exclusion principle. If the events are not overlapping, means the events are mutually exclusive, just like even number event and odd number event, then we have to use the just addition of probabilities. Now see here, one example is discussed. Consider drawing a card from standard deck of 52 cards. Drawing a heart. We know that in a deck of cards, there are 4 suits. One of them is heart. Each suit is having 13 cards. So drawing a heart card means 13 cards are the probability possibilities. So 13 out of 52 gives us 1 by 4. Now there in a deck of cards there are 3 types of face cards: jack, queen and king, and out of these face cards there are 4 king cards. So if we are interested in drawing a king card, which is our event E2, then 4 by 52, that is 1 by 13, is the probability. Now these two events are not mutually exclusive events. Why? Because the suit heart contains 1 king card. So these two are the overlapping events having 1 card common between them, which is king of heart. So the probability of intersection of these two events is 1 by 52. Now here obviously we have to use the rule which is similar to inclusion exclusion principle. Substitute the probabilities and then calculate and simplify. So with this, we will get the probability of drawing a heart king from a standard deck of cards. Now see here, it is given here in pictorial form. So there are 13 cards out of 52 cards in a deck of cards, which are the heart cards. So 13 by 52 means 1 by 4, 25%. And there are only 4 cards which are king cards out of 52. So 4 by 52 means 1 by 13, 7.69%. It is the probability of drawing a king card. And when we intersect both the events, we get the answer which is calculated in the previous example. Now, so with this, we have uh, understood the fundamental concept of probability, what is a random experiment, how to find the sample space, what are the events, what is the relationship between sample space and events, what are the 3 different probability axioms, and how we can calculate very simple probabilities as per the given data. So understanding these concepts is very important part of probability theory. And in the further lectures, we will move forward to know the concept of independent events, and then conditional probabilities, Bayes theorem, and many more. So students, happy learning.